go over. So the first thing that obviously we have to discuss is, what do we mean by mole, right? Whenever I'm saying to you guys, we're going to be talking about mole calculations. What exactly do we mean by mole? So there is a very specific definition that we can give for moles. That definition is mole is the amount of substance that contains 6.02 into 10 raised to the power of 23 particles. These particles can be atoms, they can be ions, they can be molecules, right? So the amount of substance. So moles is basically the measurement of amount, right? So I can say to you, for example, in cooking, I would say to you, all right, please do me a favor and add one tablespoon of sugar. In chemistry, we talk about the same thing, but we talk about it in moles. So moles is simply a way of measuring a certain amount of substance. How much substance? Whatever amount of substance that contains exactly 6.02 into 10 raised to the power of 23 atoms, particles, whatever. The amount that has exactly 6.02 into 10 raised to the power of 23 particles. So whatever amount of the compound has exactly this many particles, whatever amount, right? So for example, for sodium, that might be 23 grams. If I take 23 grams of sodium, that will have exactly 6.02 into 10 raised to the power of 23 particles. So that is 1 mole of sodium, right? For hydrogen, just 1 gram of hydrogen will have, for example, or just 2 gram of hydrogen gas will have exactly 6.02 into 10 raised to the power of 23 particles. So that's 1 mole. Now, so this number that you're seeing over here, right? 6.02 into 10 raised to the power of 23. This number might seem familiar to you guys as Avogadro's number. This is Avogadro's number, 6.02 into 10 raised to the power of 23, right? Now, when we are talking about your mole calculations, okay? So in your mole calculations, another concept that we have to go ahead and discuss is your formulas, right? But before we discuss our formulas, let's go over the concept of your isotopes and your relative atomic mass. What is relative atomic mass? Well, before I give you the definition, let me just tell it to you in easy terms. For example, if you look at carbon, so carbon has mass number of 12 and proton number of 6. This is, as you guys know, the proton number, and this is the atomic mass. This is what relative atomic mass is. So you will notice something very interesting. You will notice that this atomic mass, I have taught you guys that this is the mass of, for example, one sodium or one carbon atom. Now, you might question me, you might look at me and you might say, but Miss, how does that make sense? How would, for example, an atom of sodium measure 12, right? I mean, doesn't that seem like a really high value considering we're talking about atoms? So the truth is that the mass that's given in your periodic table is not the actual mass of the atom. It's relative mass, okay? So when the scientists were initially dealing with the concepts of, these calculations, there was one problem. The problem was that an atom usually has such a small mass. Like we're talking about 0.0000000000000 something, right? It has such a small mass that doing calculations proves to be trickier than usual. So the scientists wanted to come up with a way to, or come up with a standard to somehow make this a bit easier. So they came up with the concept of relative atomic mass. What is a relative atomic mass? It is basically a ratio. It is a ratio of the average mass of atoms of a chemical element so it's the ratio of the mass of atoms of an element. One second. To 1/12 of the mass of carbon-12. Quite simply put, when the scientists were doing calculations, or actually let me make this definition a bit better. It is ratio of the average mass of atoms of an element relative to the mass of atoms of carbon-12. So the scientists they wanted to standardize it. They wanted to come up with a way to make it completely, like universal, so that there was the calculations would be much faster. It would be easy to deal with all of these elements. It would be easy to do the calculations, the workings, the experiments. So they needed to figure out a standard. Okay. So they said what we will do is that we will take the mass of every single element. Okay. Sodium, lithium, potassium, calcium, and that mass of atom, whatever it is, 0.0000, whatever, we will divide it by the mass of carbon. Every single one. Every single atom in the periodic table, we will take the mass of the elements, whatever the value is, we will divide it by the mass of carbon. Okay, and this way we will end up with a standard. So every single value that is in your periodic table is actually mass of that element divided by mass of carbon. So now it is standard, right? It is standard. All of their masses are compared to carbon-12. Every single mass that we have is in comparison to carbon-12. So that is what relative atomic mass is. The number that's given in your periodic table is relative atomic mass. So it's the actual mass of the atom divided by the mass of carbon. And we will end up with a ratio, which is a larger number. This is how the scientists calculated all of the values that you see on the periodic table. Now, why did they choose carbon-12? Why not choose oxygen, right? Why not choose nitrogen? Why not choose something else? Number one reason they chose carbon-12 is because carbon-12 is very abundant, right? It's found everywhere on the earth. Number two reason is because carbon-12 is one of the few compounds whose, if you like, even if you consider all the isotopes, right? Even if you consider all the isotopes and you calculate the average, you still get 12. Okay? Meaning that carbon-12 has the highest percentage. Around 98-99% of all isotopes are carbon-12. Okay, so carbon-12, not only is it really commonly found, but it is also, if you take all the isotopes of carbon and you calculate the total mass, you still get the value of 12. So they went for carbon-12. Then there is also, we need to go over the concept of isotopes. What are isotopes? Isotopes are atoms that have same proton number but different nucleon number or different neutron number. So atoms that have same proton number but different neutron number, those are referred to as our isotopes. And when we talk about, for example, an example that I'll give you is carbon 12. So carbon 12, one isotope of carbon is carbon 12. Another isotope of carbon is carbon 13. Another isotope of carbon is carbon 14. Carbon 12 has 6 protons and 6 neutrons. Carbon 13 has 6 protons but 7 neutrons. Carbon 14 has 6 protons but 8 neutrons. Now, you are often going to be asked to do calculations about the relative isotope or the relative atomic mass. So you will be given two things. You will be given the mass of the isotope. You will be given the abundance of the isotope. So for example, let's take bromine. We have bromine 79 and bromine 81. One second. Let me actually see if I'm remembering it right. Yeah, I think these are the two isotopes of it. The rest are, yeah, okay, fine. So let's say bromine 79 is 75% and bromine 81 is 21%. So to find the relative atomic mass, we can actually do this. The formula that you're going to use is mass multiplied by abundance. Okay, so the mass is 79, the abundance is 75 plus mass multiplied by abundance. Mass is 81 and the abundance is 25%. Let's change it up. Right? You are going to divide this by total abundance. So total abundance is going to be 75 plus 25. Right? And you put everything in the calculator and you get your values. I'm sure you guys already knew how to do these calculations, but I thought I would go over them just in case you don't remember properly or for the purposes of revision. So if you do your calculations, you will see that the relative atomic mass of bromine actually comes out as, one second. You will get 79.5. So this is how you can calculate the relative atomic mass, or in fact, some examiners might say isotopic mass, but it's the same thing. So these were just some basic calculations I wanted to go over. I'm sure you guys had an idea on how to do these calculations, but I thought just in case you guys don't, I will revise it. Now, coming on to our more formulas, there are basically three or four mole formulas that are very important and that you guys should make an effort to remember. Your mole formulas include number one, the most common formula. We mostly use it for solids, but we can use it for liquids and gases as well. Okay. It's mostly for solids, but we can also use it for other substances. And the formula is moles is equals to mass over molecular mass. Okay. So let's go over simple formula. Let's say we have methane that is undergoing combustion to give you carbon dioxide and water. Right? So let's say we have been told that we are burning 4 grams of methane. And we have to find out, for example, the mass of carbon dioxide produced. Okay, normally they would ask you volume or something like that because carbon dioxide is a gas. But just for the sake of example, we can go ahead and we can let's just take carbon dioxide. Okay, even though carbon dioxide is a gas, so this is not a very good example. Or if I change the equation, 1 second, let me think about it. All right, let's just go with it. So what are your calculations going to be? First thing, look at the information available. Okay, information available is that we have the mass of methane. So let's start there. Okay, first thing is first, you're going to calculate moles of methane. To calculate the moles of methane, you are going to go ahead and start off by using the formula mass over molecular mass, right? In mole calculations, how will you figure out which formula to use? You will choose the formula that fits your data. What are the examiners giving you in the question? Whatever information is provided in the question, based on that, you are going to choose your correct formula. So over here, we have the mass. So let's use the formula for mass. So our mass is 4 grams. We have to divide it by molecular mass. You can calculate the molecular mass using your periodic table. So in the mass of carbon 12, if you open up your periodic table, you will see the mass of carbon is 12. How many carbons do we have in the molecule of CH4? Just one. Plus, the mass of hydrogen is 1 in the periodic table. And how many hydrogen do we have? 4. So we get 4 divided by 12 plus 4, which gives us 16. So the moles of methane that we are going to calculate are 0.25. After you have calculated the moles of methane, now we have to calculate number 2, moles of whatever the examiners are asking us in question. So, and the question is about carbon dioxide. So now we have to find the moles of carbon dioxide. To find the moles of carbon dioxide, we are now going to employ mole ratio. So step number 1 is you always use a formula. You choose the correct formula based on what the examiners are giving you in the question. Then you are going to find the moles of whatever the question is, whatever compound is in question. To do that, you will always use mole ratio. So step number 1, calculate the moles of the given compound. Step number 2, find the moles of the compound in question. You do that by using mole ratio. How do you use mole ratio? Oops, sorry guys, let me correct this. Let me correct the balancing, otherwise you won't get the correct answer. Now it's balanced, I think. 1 second, sorry. Yes, now it's balanced. Okay. So, number of moles of carbon dioxide, we will figure out using mole ratio. So, first thing, let's look at the moles of methane. How will you find the moles of methane are 0.25? Divide this by the moles of carbon dioxide. Well, we don't know. The moles of carbon dioxide are unknown, they're X. Okay. Then you will look at the balancing. How many molecules of methane are involved in the chemical reaction? Just one. How many moles of carbon dioxide are involved in the chemical reaction? Also, just one. Okay. So the mole ratio over here is 1:1. For one methane, there is one carbon dioxide. So what will you do? You will solve for X. You will solve for X. And you'll get the same answer. The moles of carbon dioxide are the same. They are also 0.25 moles. So wherever the mole ratio is 1:1, like it's one of each, so the moles will also be the same. But if you guys can also use this method to calculate if the moles are different. Step number 3 is find the mass of carbon dioxide. To find the mass of carbon dioxide, you can use this. You have to find the mass, right? So use the same formula. Use the formula for mass. What's the formula for mass? Moles is equals to mass over molecular mass. So the moles are 0.25. The mass we have to calculate. The molecular mass of carbon dioxide is going to be, carbon is 12 and there's just one carbon. Oxygen is 16. Where am I getting the values from? I'm getting them from the periodic table. And there are 2 oxygen. Okay. So you'll simply now solve. So mass of carbon dioxide comes out as 11 grams. Okay. So this is how you are going to do your mole calculations. So these mole calculations are pretty much going to be following the same steps throughout. Even when you're doing titration calculations, any mole calculations, follow the same steps. Okay. First calculate the, first find the moles of whatever chemical is given to you in the question. Then find the moles of the chemical that we have to calculate. So do step number 2 is using mole ratio. Then step number 3, you find whatever the examiners have asked, mass, volume, concentration, whatever. Okay. Now, so this is one question. This is one formula. The second formula is for liquids, and you will be using this formula a lot for titration calculations. For liquids, the formula that we use most commonly is concentration is equals to moles divided by volume. Moles obviously is measured in moles. The volume is measured in dm cube, decimeter cube. Okay, this is very important. Volume is measured in decimeter cube. So, and the concentration will be in mole per dm cube. So please keep in mind that you will need to convert your centimeter cube into decimeter cube. If you want to convert centimeter cube into decimeter cube, divide it by 1,000. And if you want to convert decimeter cube into centimeter cube, multiply it by 1,000. Okay. Now, these calculations are really, really important when we talk about our titration calculations. Okay. For example, let's go over a titration calculation for us. Let's take, we have sodium hydroxide. Let's react it with sulfuric acid. This is an acid-base reaction. So in acid-base reaction, we always get a neutralization reaction. So we will get sodium sulfate and water. Let's make sure our equation is correctly balanced. Okay. Then how are your titration calculations going to be? Why do we even perform titration? Titration is usually performed when we want to figure out the concentration of an unknown reagent. Okay. So the examiners say to you, for example, that we have sodium hydroxide. The sodium hydroxide has concentration of 0.2 mole per dm cube. And we are using 25 centimeter cube of sodium hydroxide. Okay. We perform the titration, and in the titration, there, for example, let's say 12.5 centimeter cube of the acid was used up. Okay. 12.5 centimeter cube of acid was used when we perform the titration. So for the neutralization point, for the end point, I will explain to you guys more about I have done with Shreya the process of titration, but I will Hajra, I will go over it again with you when we do acids and bases. So we are adding. So for us to reach the neutralization point, we needed 12.5 centimeter cube of acid. So they're saying calculate concentration of the acid. So this is why we do titration, because one of the compounds is unknown. We don't know the concentration of the alkali or the acid. So we use titration to figure it out. So first thing is first, we figure out the moles of the given. What is given? Sodium hydroxide. So let's start by finding moles of sodium hydroxide. Find moles of given. So what formula am I going to use? I am going to use concentration is moles over volume. Concentration is 0.2. We don't know the moles of sodium hydroxide. The volume is going to be, this is in centimeter cube. So let's convert it into decimeter cube. 25 divided by 1000. Okay. So 25 divided by 1000 multiplied by 0.2. So the moles of sodium hydroxide are coming out as 0.005 moles. So first, step number 1 is always find the moles of what is known. Step number 2, find the moles of unknown. Who is unknown? Sulfuric acid. So find moles of unknown. How do we find the moles of unknown? Whenever we want to find the moles of unknown, we do mole calculations. So we have 2 sodium hydroxide. Now look over here, 2 sodium hydroxide, but there is just 1 molecule of sulfuric acid. If nothing is written, that means 1. Okay. So now, how we are going to make the formula like I taught you guys previously. The moles of sodium hydroxide divided by moles of sulfuric acid. The moles of sodium hydroxide are 0.005. The moles of sulfuric acid are not known. Then is equal to, then we write down the numbers from the balancing of the equation. So there are 2 sodium hydroxide and 1 sulfuric acid. So 2 sodium hydroxide and 1 sulfuric acid. And then you solve for X, cross multiply basically, right? So we will get 0.005 divided by 2 is equals to X. So the moles of sulfuric acid are coming out as 0.0025. So now we have the moles of unknown. After you find the moles of unknown, you're going to find whatever the examiners have asked you. So if the examiners have asked you concentration, now you find the concentration. To find the concentration, again, we have the moles. So, and we have the volume. So there's only one formula of concentration that you guys know, and that is concentration is equals to moles over volume. We have to find the concentration. The moles are 0.0025. The volume is 12.5. Again, this is in centimeter cube, so let's convert it into dm cube by dividing it by 1,000. And the concentration of the acid comes out as concentration is going to come out as 0.2 mole per dm cube. So this is how you're going to do your titration calculations. Start by finding the moles of the known, then find the moles of the unknown, then find the whatever the examiners have asked you in the question. Okay, concentration, volume, whatever is part of the question. You're going to calculate that accordingly. Just give me 1 second. Now, the third important formula that we have to go over is the formula for gases. The formula that we can use for gases is moles is equals to volume divided by 24 dm cube. What is this value, 24 dm cube? Well, this value of 24 dm cube is known as molar gas volume. Simply put, it is the volume of gas, or volume of 1 mole of gas occupied at room temperature and pressure. Okay, what is molar gas volume? Molar gas volume is the volume that 1 mole of gas will have. So if you take 1 mole of carbon dioxide, 1 mole of helium, 1 mole of hydrogen, so you will always end up with this volume, 24 dm cube. So any gas, it doesn't matter. Any gas will, if you have 1 mole of any gas, it will always have the volume of 24 dm cube at room temperature. So this is what the value is. This is where the scientists got the value of 24 dm cube. Now, you can use this once again. The calculations are going to be in the same way I've taught you guys earlier in the chapter. For example, let's say that we are doing a thermal decomposition reaction. So we have magnesium carbonate, which is breaking down to give you magnesium oxide and carbon dioxide. You have been told that the mass of magnesium carbonate, that the mass of magnesium carbonate is, let's say, 6 grams. Okay, we have to calculate the volume of carbon dioxide produced. Actually, just give me 1 second. Let me see if we can. 1 second. Let's change the equation. 1 second. Let's do magnesium reacts with steam to give you magnesium oxide and hydrogen gas, or 1 second. All right, so this is a reaction that we studied when we did the topic of metals, right? I told you guys that metal can react with acid to give us salt and hydrogen gas. So the mass of magnesium is 6 grams. I'm going to make this question slightly tricky for you guys. I am also giving you guys volume and concentration of hydrochloric acid. The volume of HCl that we're using is 25 centimeter cube, let's say. And the concentration that we're using is, for example, let's take 0.2 mole per dm cube. Okay, you have to find the volume of hydrogen gas produced. Now, automatically, you might get another question in your head. Right now, looking at this, you might be wondering that, Miss, we also have the information regarding magnesium And we also have the information regarding hydrochloric acid. Which one do we use? You taught us the method that calculate the moles of known and then find the moles of unknown. Over here, we have two chemicals that are known. So which chemical should we use? So how are you going to do that? You will find moles of both. Okay. First, you're going to find the moles of magnesium. Magnesium has the mass. You're going to use you have the mass. Mass is given, right? So we will use the formula of mass. Mass over molecular mass. So moles is equals to mass is 6 grams divided by molecular mass. Your molecular mass or MR that we can use is, if you guys, I think it's 24. Please check the periodic table and let me know if I'm wrong, but I think magnesium is 24. So 6 divided by 24 is going to give you 0.25. Okay. After you find the moles of magnesium, now find the moles of the acid. You have the concentration and volume. So we are going to use the volume. Concentration is equals to moles over volume. The concentration is 0.2. The volume is 25 centimeter cube. So divided by 1,000. So the moles are going to come out as 0.005. Now, you must be wondering, Miss, but why? Why are we calculating magnesium and also HCl? There is a reason, okay? The reason is this, that in every single mole calculation, okay? Actually, I'm going to change the value a bit, sorry. Let's change this to 0.3. So 25 divided by 1,000 multiplied by 0.3. So we get 0.075. Let's go. So you must be wondering, Miss, why are we also calculating the moles of magnesium and also hydrochloric acid? I mean, what are we even doing right now? The reason we are calculating the moles of both magnesium and hydrochloric acid is in that in chemical reactions, normally we have one reagent that is the limiting reagent and one reagent that is always in excess, right? In exam questions, sometimes they will actually tell you that we added the acid in excess. This was added in excess, right? So in most chemical reactions, we can have a limiting reagent and we have another chemical that is always in excess, like there's too much of it, more than required. So in all mole calculations, in all mole ratios, we want to use the limiting. We never, ever, ever want to use the excess. Okay, so that's the issue right now. The issue is this, that we also have information about magnesium and also about hydrochloric acid. But we need to figure out which one of them is the limiting reagent. Okay, so the moles of magnesium are 0.25. The moles of HCl are 0.0075. We are not done yet. I'm not done with the calculations yet. I'm not done with the calculations yet. Why am I not done with the calculations yet? Because you will see over here that the moles of HCl or the balancing of HCl is 2. Okay. So we want to divide this by 2. Okay. We always want to find the value for 1 mole. Remember this, whenever the examiners give you 2 reagents and they say which one is in excess, which one is limiting, always find the value for 1. The value that we got for HCl is for 2. So we have to find divided by 2 and get the value for 1. So we get 0.00375 moles. So now we can see, now you guys can see that who is in excess? Who has the larger value? Magnesium. So magnesium is in excess. There's too much of magnesium. Sodium hydroxide is our limiting reagent, meaning that the reaction depends upon sodium hydroxide. Sodium hydroxide is in lesser quantity. Once sodium hydroxide is used up, that's it. Reaction finishes. Okay. So wherever the examiners will give you two chemical compounds, two reactants, and they will say to you that please find out who is in excess or who is the limiting reagent. So calculate the moles of both. Okay. Then divide it by the balancing to find the value for 1 mole. And whoever has the greater number of moles, they are in excess. So who will I use? Will I use HCl for calculations or will I use magnesium for calculations? I will use HCl. Okay. I will use HCl. We always use limiting reagent is used for mole calculations. So the moles of sodium hydroxide are 0.00375. So now we will simply use the mole ratio and find the volume of hydrogen gas. So to find the volume of hydrogen gas, we will use the formula moles is equals to volume over 24 dm cube. The volume moles are 0.00375. I did not do mole ratio over here. Why? The reason for that is because when I divided the value by 2, I had already basically done that. Okay. Because I divided it by 2, so I made it 1, and this is also 1. So I skipped the step basically. Okay. So the moles are 0.00375. The volume we have to calculate, and this is 24 dm cube. So you are going to simply multiply the value by 24. So you will get the volume is going to be 0.09 dm cube. So this is how you're going to be going for your mole calculations. Normally, it's not going to be as tricky as I've given you in the questions. I'm obviously trying to teach you multiple things in one attempt, right? The examiners will break it down. They will say, calculate the moles of magnesium, calculate the moles of HCl, which one do you think is in excess, right? Like that. Okay. So they will give it to you as multiple questions. I explain it all in one question, so it seems more confusing, but the examiners will give you step by step. Who is the limiting reagent? Who is in excess? And then when they ask you to do mole calculations, you always use the limiting reagent. Right? Is this making sense, guys? I know it's a bit confusing, but I hope it's making sense somewhat.
Yes.
Shreya, is this making sense? Okay, all right. Okay, so I think for today we will go ahead and stop it over here for today because we have done a lot of new stuff that is quite a lot. So I think we will stop it over here for today. And in our next class, we are going to go over our calculations for water of crystallization. Okay, we will go over our calculations of percentage yield, percentage purity, percentage composition by mass, and I think we also have to take a look at empirical formula. Okay, so we will go ahead and take a look at all of that in our next class. Okay. Okay, all right. Thank you so much, guys. I'll see you both in the next class. Have a good day. Bye, guys.
Assalamu alaikum, yes.
Assalamu alaikum, Aram. How are you?
Good, alhamdulillah.
Okay, Aram. So we were going over our questions on Group 1 and Group 7. So let's take a look at our questions. Give me a second to share the screen with you. Hold on.